Okay, I'm going to go through the solution for Chapter 12, Problem 45. This is a classic kind of fluid dynamics problem. We have a moving fluid in a pipe. So let's read through the problem. We have at a certain point in a horizontal pipeline, the water speed is 2.5 meters per second, and gauge pressure is 1.8 times 10 to the fourth pascals. We want to find the gauge pressure at a second point in the line if the cross-sectional area at the second point is twice that at the first. Okay, so read through that problem, maybe read through it a second time, and then let's solve use our normal problem solving method. We want to draw a picture, write down our knowns, figure out which concept is relevant, and then use those concepts to solve for any unknowns. Okay, so I have a pipeline. So here's a pipe. And at a certain place in that pipe, we'll call that spot point 1. At that point in the pipe, we know the velocity at that point in the pipe is 2.50 meters per second. And we know that the gauge pressure, gauge pressure at point 1 is 1.80 times 10 to the fourth pascals. Okay, and then at a second point in the line, the cross-sectional area is twice that of the first. Okay, so we have a pipe which is going to get bigger. Okay, so at point 2 in the line, the water is still flowing in this direction, but the cross-sectional area at point 2 is bigger. All right, so there's some cross-sectional area of this pipe here, A1, and there's some cross-sectional area of the pipe here, right, that's A2. And so it tells me that the area at point 2 is twice that of the area at point 1. All right, so the cross-sectional area where point 2 is twice that at point 1. Oops, sorry. Twice that of A1. So I can take that, what the problem told me in words, and write that in equation form. The cross-sectional area at point 2 is twice that of the area at point 1. Okay? I do not know the velocity of the fluid at point 2. I do not know the pressure of the fluid at point 2. So I have those two unknowns. Okay? And this is what the problem is asking. It wants to know what is the pressure at point 2. Okay. So we've drawn a picture, we've written down our knowns. Now let's think about what concepts we have to include here. It wants us to know the pressure at point 2. To understand that, we need to actually bring in two concepts. First, what happens to a fluid as the pipe gets bigger, right? We know that the flow rate in this pipe has to remain constant. If I put 1 gallon in one side of the pipe, a gallon has to come out the other side of the pipe. Okay, so saying that in words, saying that in equation form is saying that the volume flow rate, so this is capital V, the amount of volume per unit time passing a given point at point 1 has to be the same amount of volume at point 2. Right, so dV dt is just a symbol for volume flow rate. Right, the amount of volume passing a given point in a given period of time. So this is our continuity equation. This is a really important concept. It's a completely full pipe. Water is a completely incompressible fluid. So if I put a gallon on this side, there's nowhere for that water to go. A gallon has to come out the other side. Okay. I also know that as the cross-sectional area changes, I can rewrite my volume flow rate in terms of the area of the pipe and the velocity of the fluid. All right, so I can rewrite the continuity equation in this way. All right, so both of these equations will be on your equation sheet. So this equation tells me that as the area of the pipe gets bigger, if A2 is bigger than A1, that means V2 must be smaller than V1, meaning as the water flows from point 1 to point 2, it must slow down when the pipe gets bigger in order to keep the flow rate the same. All right, so that's an important concept. So we're going to use this to solve for V2. Right, I can solve this for V2, and that will enable me to figure out this unknown. And then how do I plan to figure out the pressure? Well, to figure out the pressure, I'm going to use Bernoulli's equation. Right? I know that if the water moving from point 1 to point 2 is slowing down, conceptually that means that it's losing kinetic energy. Right? If it's losing kinetic energy, it's slowing down. Where is the energy going? Well, there's only one place it can go, and that's an increase in pressure. Remember, pressure is an energy density. So we know that the pressure is going to increase. Right? Whatever our answer here has better be bigger than this. Okay, so that's kind of the conceptual understanding of what we're going to do here. So first, let's solve for V2. V2 is equal to A1 over A2 V1. I know V1 is 2.5 meters per second, and I don't know A1 or A2, but I know their ratio, right? This equation tells me that A1 divided by A2 is equal to 1/2. Okay, so I can plug that in here. I have 1/2 times V1, 2.50 meters per second. So that tells me V2 is just equal to 1.25 meters per second. Okay. The area got twice as big, and the fluid had to slow down by half. Okay. So I now know the velocity at point 2. Okay, and I know that means the kinetic energy is smaller now. So this tells me I should use Bernoulli's equation. That's the next big concept. Anytime you have a flowing liquid, we almost always use Bernoulli's equation to solve the problem. So Bernoulli's equation we can write down from our equation sheet. Okay, so this is Bernoulli's equation. It's basically telling me that this quantity is constant. The pressure plus the gravitational potential energy density plus the kinetic energy density, this quantity as a whole has to be constant, meaning at point 1, this quantity has to be equal to the same thing at point 2. Right, so in this case, if the velocity is getting smaller, right, if this term is smaller than this one of these terms had to get bigger, right? And the height's not changing, so that's telling me the pressure is going to have to get bigger. This is going up because this is going down. Okay, and we're going to be able to use this equation to solve for P2. It's an energy conservation formula. Okay, and these two terms are just going to cancel out. Why is that? Because point 1 in this pipe and point 2 are both in the middle of the pipe, and the pipe hasn't changed in height. So y1 is equal to y2. Right? There's no change in the gravitational potential and energy density. Okay, so these two terms I can just cancel. So I want to solve for P2. P2 is equal to P1 plus 1/2 our density times V1 squared minus V2 squared. Okay. So I skipped one quick algebra step there, but I think you can find that solution. And now we know everything. We know the gauge pressure at point 1 is 1.8 times 10 to the 4 pascals, plus 1/2. They didn't tell me the density of water in the problem. I can look that up. It's 1,000 kilograms per cubic meter. Okay, it just says water in the problem. It's not seawater or anything like that, just water, so 1,000 kilograms per cubic meter. And this is 2.5 meters per second squared. That was our initial velocity minus 1.25 meters per second squared, which was our final velocity at point 2. And plugging this all in, I get that the answer is 2.03 times 10 to the 4th pascals. Okay, so that's the answer they're looking for. The pressure at point 2 is higher than the pressure at point 1. The water slowed down, the kinetic energy went down, the energy had to go somewhere, it went into an increase in the pressure. So the pressure at point 2 is bigger than the pressure at point 1. And so the pressure at point 1 was 1.8 times 10 to the 4th pascals. At point 2, it's 2 times 10 to the 4th pascals. Okay, and I'll quickly note that the problem asked you about gauge pressure. Okay, let's just do a quick reminder of what gauge pressure is. Right, gauge pressure is the pressure that a pressure gauge would tell you that has been calibrated to read 0 when something is at atmospheric pressure. Okay, so if I know the gauge pressure and I want to know the absolute true pressure, I need to take the gauge pressure and add to that the pressure of the atmosphere. Right, this is the standard 1 atmospheric pressure. If I add to that the gauge pressure that I read in my pressure gauge, that tells me the true absolute pressure in pascals. Okay, I didn't have to deal with converting between gauge and absolute in this problem. I can keep everything with the pressure, the gauge pressure. Why is that? Well, they told me the pressure and the gauge pressure. They want the answer in the gauge as gauge pressure, and Bernoulli's equation is just telling me about pressure differences, right? Here I'm just finding that the difference between P1 and P2, I could rewrite this in another way, P2 minus P1, the pressure difference is just equal to this value, 1/2 rho V1 squared minus V2 squared. Okay, so since both of these are gauge pressures, that's totally fine. All right, it's just asking me about the change in the pressure. So there's your answer. Thank you.